If you haven't already, I'd like you to try this one out. Our goal here is to find a power series for the arctangent of x, and the hint I want to give you is see if you can use derivatives or integrals to help you out here. Alright, so for this one, I definitely don't see a fraction going on, so no obvious way to make this equal to a over 1 minus r, but I do know what the derivative of my function is. So the derivative of arctangent is just going to be 1 over 1 plus x squared. Okay, so that could be useful. Let's see if I can come up with a power series for 1 over 1 plus x squared. So our easiest way to do that is to set it equal to a over 1 minus r. So let's see, what are a and r? Looks like a is 1. R is going to be negative x squared. So my power series for the derivative is apparently a times r to the n. So 1 times negative x squared to the n. Or if you want to write that a little bit differently, just to kind of simplify it a little bit, negative 1 to the n times x to the 2n. Okay, so remember I wasn't actually looking for a power series for the derivative, but this is going to help me get there. So to get my actual function, what I need to do is integrate both sides. So to find the arctangent of x, I need the integral of g prime of x. So that's going to be the integral of this power series. So let's try that out. That means the arctangent of x is going to be equal to negative 1 to the n times x to the 2n plus 1 over 2n plus 1. Don't forget, I need to add a constant out front. Alright, so let's see what that constant's going to be. In general, what I want to do to find the constant is plug in the center of that series. So in this case, the center is at 0. So let's go ahead and plug in 0. Zero raised to just about any power is going to be 0. The only time it wouldn't work out that way is if I did 0 to the 0, which is 1. Well, since I'm starting at n equals 0, I start with 0 to the 1, so that never happens. So everything in that series just turned into 0. Now I just need to think about what the arctangent of 0 is. Well, let's see, I'm thinking which value of tangent gives me 0? Ah, it would be this value here, which is 0. So once again, and it often works out this way, but not always, I found that c is equal to 0. So finally, to write my answer here, using what I now know about c, I've got the sum from 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1. Okay, and if I wanted to write out the first few terms of that, just to kind of show you what it looks like, it's going to be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, etc. Notice we're just doing the odd numbers, so we've got an odd exponent and an odd denominator, and we just keep going up by odd numbers. Okay, so kind of surprising that I get such a nice looking series for a function crazy like the arctangent of x. Okay, so this wasn't part of the problem, but one of the interesting consequences I want to show you about this is that we now have figured out an effective way to calculate what pi is. Okay, so aside from just looking up on a computer what pi is, people actually have to calculate what it is. And they don't do it by actually measuring circles and figuring out the ratio of the radius and the circumference. Instead, what they do is they take a power series like this to calculate it. So if I wanted to find pi, okay, the easiest way I could do that with what I just found is 4 times the arctangent of, 4 times, let me write it a different way, pi over 4. Now the reason that helps us is because pi over 4 is the arctangent of 1. Right? If I was thinking about the question, which value of theta gives me tangent of theta equals 1? That's over there at pi over 4. Okay, so if I was going to find pi then, I would do 4 times the arctangent of 1, but to find the arctangent of 1, I'm just going to take this series and plug in 1. So let's try that out. 1 minus 1 cubed over 3 plus 1 to the 5th over 5 minus 1 to the 7th over 7. So keep on going as many terms as you want in that series, and the more terms you go, the more accurate you're going to get an estimation for pi. So if I had to gather like 1,000,000 terms there, I will have a great approximation for what pi is. The more terms I add, the better it gets. So this is actually a sneak peek into how people actually calculate pi with precision. Turns out this is not one of the best power series to use to calculate pi. There are other ones that do what's called converging faster, but this one does work, and it's one of the first ways people were able to calculate pi with great accuracy.